That's all. So start it up again. Yeah,
Okay.
this one is for like the actual iPad. The top speaker is like speaker for the iPad.
Gotcha. Okay.
The green obviously.
Pretty loud. That means it's clipping probably. So we're gonna bring it down a little bit. Depends on how loud he speaks. It's a little warm in here. There's two cameras, just so you know. There's the live stream camera, which is that one, and then this one's like for the recordings for later. Yeah.
And I don't need to do
As you're
anything on that
projecting,
one.
what's that?
I don't need to do anything on that one.
I'll show you whatever you need to know. I don't know about
Okay.
that. But this one should be pretty easy once you get it going. I think we're ready. Do we take the mic off? Yeah. So we're recording now.
Okay.
Really don't have to do anything at this point.
I'm just
Except
gonna
turn it
go
off.
back to.
Yep. I'd go in a little bit just because
Okay.
it's only 1080, so it's not like they can. It's not the highest definition. So when you turn it off, end event. That's the only option, and then hit done. It just charges that pad up a little bit. We'll plug it in this way.
Okay.
It's the bottom one.
Oh, my bad. I knew that. Thank you.
No problem. I think we're ready when you are, so
That is the noise from the mic.
try to project into that mic in front of you. Just for the rooms, people in the back of the room can hear you. Yeah.
Good morning, everyone. My name is Sean Kilgallon. A little bit about me. I'm a postdoc researcher at UD as of 2 months ago. I graduated this summer from the Institute for Financial Services Analytics. So my research is all about cybersecurity, using large-scale machine learning for the detection and classification of malware. So this paper is entitled Magic, Malware Analysis to Generate Important Capabilities. So this paper is all about using malware analysis and machine learning to predict a malware's capabilities before it's run in a sandbox environment. So normally, you would find a malware's behavior by running it in a sandbox. You can see its behavior, what kind of capabilities it has. But in this paper, we're trying to use fast static analysis to predict that without actually having to run the malware. Also, I'm a lead data scientist in a cybersecurity company called Cyber 2020. So a lot of my research goes into improving the platform. So if you have any questions at the end or during about the research or the company or my work, feel free to ask questions. All right, so let's get started. So talk a little bit about the major problems in cybersecurity research. One is that there's millions and millions of malware out there currently. As of last year, 700 million malware variants are out in the wild. And right now, I think 1 million or so malware variants are being released every day. That also coupled with malware becoming increasingly more complex. So malware that tries to predict whether or not it's being seen or being tracked in a sandbox environment, things like that. Number two being the scarcity of data sets. So there's really no singular place to go and find malware to do malware research. So there's VirusTotal, which a lot of people use, but it's really hard to get actual malware files from there. So we actually partner with a company called Reversing Labs, in which we get a huge malware stream. We're downloading tens of thousands of malware every day and running that through our analysis platforms. And then that brings me to dynamic analysis. So dynamic analysis would be taking a malware file and running it in a sandbox environment, seeing its behavior. So that's really good in that you can actually watch the malware perform its malicious behavior, you can know its capabilities, but it's expensive. So you have to run a malware, say, anywhere from 30 seconds to 5 minutes in a sandbox environment. If you're trying to analyze 100,000 malware. That's going to take a lot of time and a lot of resources. So we're trying to come up with ways of circumventing that. So today I'm presenting our magic model, which leverages fast static analysis to decrease the time of needing to run dynamic analysis. And so what we use is assembly analysis, which is our most complex form of malware analysis or static malware analysis. So we know what kind of instructions the malware passes to the Windows operating system, and we can map those instructions to specific capabilities of the malware, or that's our intention. One of the key pieces we decided early was to use highly interpretable and easy to visualize machine learning models. One, to provide that to threat intelligence people and organizations. And two, people like to know why the decisions are made in their company. So more complex machine learning methods such as neural networks might be more accurate, but also don't provide any sort of feedback on why the decisions are being made. So in this project, we decided to use decision trees. So I'll show you an example of that on the last slide. So the first thing we have to do is talk about static characterization or static analysis of malware. So static analysis can range anywhere from looking at the distribution of bits in the file, or looking at the strings of the file, all the way down to assembly analysis and looking at the source code. So in this specific example, we're using a tool called Radar 2, which is a disassembler and a reverse engineering tool. So basically, we can take that malware binary, we can reverse engineer it, and try to get a source code tree from that. So there's 3 different levels of source code that we can look at. We can look at a function level, basically a control flow graph or an instruction, or all the way down to the instruction level. So the 3 different types of granularities. We chose to do control flow graphs, which comes at the block level, which gives us a granularity that we like. Function level, there can only be, sometimes there's only one node in the source code tree. At the block level, there tends to be hundreds. At instruction level, you can have a graph that's 20,000 nodes. It's really complicated to understand. So one of the features that we use is an instruction histogram. So we have basically all of the instructions that the binary will execute over its life, and we construct a histogram of that. And it's basically a simple table. So that becomes one of the inputs that we can use for machine learning. Another more complicated way that we can use this information is if we just use, say, an instruction histogram, we lose a lot of the information that's in the graph. So what we decided was maybe we'll do a random walk of the graph. So we'll start at the start position, or where the source code starts to execute, and we construct a random walk. So this is just one walk of 5 nodes. So basically, every node is a block or a set of instructions. So we basically construct a feature vector that's a set of instructions, a set of instructions, a set of instructions, 5 wide. And so this gives us 5 instruction histograms. That gives us a little bit of detail about how the source code tree was designed. And then we construct the feature vectors from that walk. So the next thing we have to actually decide is what capabilities each malware has. And we can find that out by actually doing dynamic analysis, or taking that malware and running it in a sandbox. So there's actually 2 ways we do that. The first way is we have a partnership with Reversing Labs, where we get our malware data. They also curate it. So we have indicators of interest, which basically provide us buckets of capabilities. Also, we have a dynamic analysis platform we run on AWS. So that's running Cuckoo, which is an open source sandbox environment. It's also, they also partnered with MITRE, which is a large corporation, normally handles government contracts. They actually started this set of capabilities called MIC, or Malware Attribution and Enumeration Characterization, I think it stands for. But basically, they wanted to create a set of messaging protocol that they could send if they, say, a cyber intelligence team finds a malware and wants to send it to another organization, that they might also see that malware. So information can be passed from organization to organization. So basically, we can run our malware through this Cuckoo cluster. We can also look up indicators of interest here, and we can get our targets. So this are our MIC capabilities bucketed. So things like anti-behavioral analysis. So anti-behavioral analysis would be something like the malware checks its browser history of the Windows machine. If there's no browser history, it's most likely a sandbox. It can do things like, if it's only run on one core, it's mostly likely a sandbox. Things like that. We want to prevent against, if we know the malware is anti-behavioral before we run it in the sandbox, then we can maybe run it on a bare metal system in which there's no sandbox environment, so the malware will run completely and fine. Things like that. So the indicators of compromise from reversing labs are bucketed. There are basically major categories which have subcategories, and so we construct models for the major categories. So our data set for this paper, actually, there's two sizes. Our Cuckoo size is around 6K malware, because we had to run the malware ourselves on our own clusters. Our A1000 data set is around 60,000 malware. And they come from 9 different malware families. Now this data set is all financial malware, so malware targeting either financial organizations or personal banking information. And the counts of the capabilities are in these 2 columns. So we chose to use decision trees because they're highly interpretable and they're easy to visualize. And we can basically point to the decision trees and say why they're making the sure. Just a quick question, what is A1000? So A1000 is reversing labs analysis cluster. So Cuckoo would be our dynamic analysis platform, A1000 is the third family. Good question. So also it inherently performs feature selection and importance. It's very low computational cost. We can train all of our decision trees in less than 2 minutes, I think. And then most importantly, we can identify instructions that lead to specific capabilities. So looking at our decision trees, we can make, we can recognize patterns and things like that. So the results, these are the results of the A1000, or the indicators of compromise, or indicators of interest. So our lowest accuracy is around 86%, our highest being 96%. But across the board, they perform very well, especially using decision trees, which is a very simplistic machine learning algorithm. Moving on, our Cuckoo results are bucketed, so there's only 7 categories. They also range from around 86 to 97%, which leads us to believe that both sets of capabilities are similar. The results from this basically allow us to make some predictions, and those predictions basically allow us to use fast static analysis that we can complete within I don't know, 10 seconds, 5 seconds, to predict important capabilities of the malware that we would normally have to run it in a sandbox for upwards of 5 minutes. Potentially, it would never show to be able. Also, if we can identify malware that's anti-sandbox, or trying to predict whether it's being watched, we could use something like a bare metal system. So that's just a computer with Windows installed on it with some sort of supervisor that's watching the malware. So it can't determine that it's in the sandbox if it's not in the sandbox. Also allows us to spot anti-detection malware, which might require more sophisticated machine learning techniques or more sophisticated analysis techniques. So this would be an example of our decision tree model. So all of these splits are actually instructions. So this comes from a binary global instruction histogram, which means we take all the instructions from the malware, construct a histogram, and then we basically say whether or not that instruction exists in the program. And so we could say, you know, if it has the roll command, we go down. If it has cmove, yes, it does have this capability. So these types of patterns are really interesting for cyber analysts or threat hunters in organizations that have lots of information but they don't know what to do with it. So we thought that this might be interesting for cyber analysts, especially if they're going to senior management and trying to justify their actions. Sure.
Are you including complex instructions in this, or just simplified instructions?
Just simplified instructions for now.
Okay.
But this is extendable to pretty much any instruction. We just mapped, I think, 40 instructions or so,
Okay.
and then counted from the source code.
Thank you.
Any other questions? That's it.
Yeah, so I've got a question just about the main use case for this.
Sure.
Because it seems like you're not including like normal files, so it's not determining whether or not it's malware. You're determining the capabilities of the malware.
Right.
So I would think that like if I came across a single malware file and I was interested in investigating it, I would just kind of run it through dynamic analysis first and just see what happens there.
Right. Yeah. So this has kind of two use cases.
Okay.
One is this would happen after malware detection, probably at the same time during malware family classification, because basically predicting capabilities is all about what the malware does. You want to know if it's ransomware versus a spam bot, because a spam bot's just going to spam your email. Ransomware is going to encrypt your entire system. So knowing that capability, when you detect that it's malware, will determine how you remediate the malware as well. The other use case is basically to quickly determine malware's capability without running dynamics. So 5 minutes may seem like not a lot of time, but if it's a ransomware, 5 minutes can do a lot of damage.
I guess one more question. Yeah. So you mentioned virus total, and as you know, like malware writers frequently test their code against virus total for this. So I mean, if this becomes more prominent and it gets used in important like security programs,
Absolutely.
like they could start to also change the number of jump instructions, for example, it's a different type of malware.
Yeah, absolutely. I think one of the biggest emerging topics in cybersecurity research is adversarial. And there's a lot of work being done in adversarial machine learning in terms of like image recognition, but this is the scary portion of adversarial machine learning. I mean, if the leading organizations use machine learning to do cybersecurity threat detection, there's ways around that. there's ways to attack machine learning models. So yeah, that's a big problem, especially using a simplistic model like this.
You said there were like 40 instructions that you consider?
Yeah.
Are those automatically, did you determine that those are the highest confidence?
Yeah, so I think we just took a list of all the malware that we currently have and all the assembly instructions that we currently have, and we picked like the top 50 or 40 most frequent instructions. Did that. But yeah, good question.
Did you also do something with like multi-dimensional analysis to determine like, this might be the most common instruction, but maybe it's not a very good differentiator?
Yeah, so that's why we were using feature, where we're using decision trees, because it inherently does that feature selection portion. But it's definitely, the data that we're using for this is simplistic because we wanted to visualize it. But if we wanted to extend this, we could use things like distribution of bits in the file, byte entropy histograms, we could use lots of information. Any more questions?